As we discussed in the last video on an overview of concepts of the course so far, we said that valence electrons are important in determining the three-dimensional structures of molecules. Molecules are made of atoms, and they have a three-dimensional structure just as any other object has a three-dimensional structure. The valence electrons are those electrons that are present in the atom in addition to the electrons present in the previous noble gas. For example, helium has 2 electrons. Lithium has 3. Lithium has 1 more electron than the previous noble gas, so it has a valence of 1. Beryllium has a valence of 2. Boron, 3. Carbon has a valence of 4. Nitrogen, 5. Oxygen, 6. And fluorine, 7. Now, all of the elements in this period have a valence of 7. All of them in this period have a valence of 6. Phosphorus, just as nitrogen, has a valence of 5, and so forth. So let's determine, first of all, the types of compounds that can form in chemistry and the shapes of the compounds. First, let's go back and say one more thing about the elements. The elements on this side of the table are metals. The few elements, there's a zigzagged line in your textbook or you can find on Google. The elements to the right of that are nonmetals. And the elements along the zigzagged line, like silicon and germanium, are called metalloids or semiconductors. So nonmetals on this side, metals on this side. Now the most electronegative element in the table is fluorine. It's the smallest and the most electronegative element, meaning that it has the greatest desire to gain an additional electron, and it has the lowest desire to lose an electron. And that concept of losing an electron is called ionization, and the energy required is called ionization potential. So if you remember that fact, that fluorine is the smallest and most electronegative element, you can answer questions like this. Which is a larger element, bromine or chlorine? Bromine is larger. As you go up and across the periodic table, you get smaller until you get to fluorine, which is the smallest. If you look at phosphorus or nitrogen, phosphorus is a bigger atom than nitrogen. As you go up the periodic table or to the right, you get more electronegative and smaller. How about sodium or magnesium? Magnesium must be smaller, aluminum smaller still, chlorine smaller still, fluorine smaller still. Now, there are a couple of types of bonds that we talked about, 3 in fact. One of them is called an ionic bond. These are developed between atoms on the far left, which are metals, and atoms on the far right, which are nonmetals. An example of this is lithium chloride. Lithium, as we stated, likes to lose 1 electron to look like helium. And when it does that, it itself, because it has lost a negative charge, becomes a positively charged atom. And chlorine likes to gain electron to become like argon. And when it does that, it becomes chloride. Lithium chloride is an ionic compound. In a crystal, it's composed of lithium plus and chloride minus atoms, ions, and it conducts electricity when you put it in water because these charges can help move charge. This is an ionic compound. Now, compounds like water, this is not a metal, nor is this a metal. These are both nonmetals. And a compound like water is composed of covalent bonds. And these are bonds which share electrons rather than donate electrons from one atom to another. And then there are bonds called hydrogen bonds. Hydrogen bonds are very weak And they exist when it is fun to do so. And by that we mean a hydrogen bond could exist, for example, between hydrogen fluoride and water because the hydrogen can exist between oxygen and fluorine. Another example of hydrogen bond would be in ammonia and water, because again, the hydrogen can exist between oxygen and nitrogen. And so hydrogen bonds tend to cause molecules to associate. It helps them dissolve, and it can increase their boiling points and so forth. Let's spend a few moments discussing how we determine molecular shape. Let's look first of all at borane. Now boron has 3 valence electrons, and we're just going to put those right here. Hydrogen has 1 valence electron. Now I already know the answer to what this molecule looks like. So I'm going to show you that this molecule has a triangular shape. The reason I say that is we have 3 entities around boron. As we said, atoms like to be close together, but not too close together. So they've come together to bond. They've formed 2 electrons, makes a bond. Now I'm going to draw this hydrogen down here. It's the same molecule as the one above. They like to be close together, so they've bonded, but they don't want to be too close together. And the way to get 3 things as far apart as possible is to put them into a triangle. So borane is triangular. Now let's look at another one. Let's look at methane. Now notice in borane that we had 6 electrons around the central atom. 2, 4, 6. But there's the octet rule, and this means that most atoms, when they bond, want to have 8 electrons around them because they will look more like a noble gas. So if we look at methane, now we have 8 electrons around the carbon. The octet rule is satisfied. It turns out that the way to get 4 things as far apart as possible in space, which we want to do, is to put them in the shape of a tetrahedron. And I should have brought the model to show you on the screen. I'll do that on the next, later on when we talk about shapes. But the shape of this molecule is tetrahedral. Let's do a couple of others. Water. Oxygen has 6 valence electrons. Let's just put them like this. And it has 2 hydrogens. Water has 1, 2, 3, 4, 5, 6 valence electrons. Now, what do we have? We have 8 electrons around the central atom, so the octet rule is satisfied. We have 4 things in space that want to get as far apart as possible. So we must be dealing with a tetrahedral shape. And the electrons are in 2 corners of the tetrahedron, the hydrogens are in the other 2. Because when we look at a molecule we don't see the electrons, we only see the atoms, water is bent. The structure is bent, and the geometry here is about 105 degrees. I didn't mention it before, but the geometry of a tetrahedron is about, I think it's 109 degrees between the different atoms. One more, we'll look at carbon dioxide. Carbon dioxide, again, carbon has 4 valence electrons. Oxygen has 6. So if we put the electrons, I know what the answer is going to be, so I'm going to put it like this. If we put the 1, 2, 3, 4, 5, 6 1, 2, 3, 4, 5, 6. Now we have 8 around oxygen, 8 around oxygen, and only 4 again around carbon. So I'm going to take these two and put them here, and those two and put them here. And now this looks like this. I'm going to put the 4 carbon electrons there, and I'm going to put the 6 oxygen electrons like this. Again, I know what the answer is already, so that helps me. But I showed you one mistake sort of you can make. Now we have 8 electrons around carbon, 2, 4, 6, 8 around each of the oxygens. So if we draw, since each pair of electrons is a bond, now we have a carbon with 2 double bonds. Now, to get two things as far apart as possible in space, we don't have any electrons over here, we just have 2 entities. We put them in a straight line. So carbon dioxide is linear.